introduction to exponential functions. So the exponential parent function, the one that is used the most often, is y equals 2 to the x power. So what makes something an exponential function is the fact that we have a variable in the exponent spot. None of our other functions do that. Now, the general layout is this f of x equals a times b to the x power. So the a, that is your initial value, which is simply your y-intercept. Then the b to the x, whatever has that exponent of an x on it, that is the growth or decay factor. And we'll talk more about that in just a moment. So the number without the exponent is the initial value, and the b to the x, whatever is attached to that exponent, is the growth or decay factor. Now there's two types of exponential functions. Exponential growth, which increases from left to right on a graph. It has a b value greater than 1, so that number that is attached to the x exponent has to be something greater than a 1. So for example, we have y equals 1/2 4 to the x. So the 4 is what we decide is this growth or decay. So since the 4 is greater than 1, we call this a growth. Here's another example. There is an a value in the front, but it's just a 1. 3/2 to the x. The 3/2 is what's attached to x, so that's our b. And 3/2 is greater than 1. Yes, it's a fraction, but 3/2 is really 1.5. So it is greater than 1, which makes it growth. The second kind that we have is exponential decay. This function decreases from left to right on a graph, and your b value is less than 1, but not negative. So 0 is less than b, which is also less than 1. You don't have b values that are negative, so it's either greater than 1 or it's smaller than 1. So some examples. 2/5 to the x, 3 times 2/5 to the x. So this 2/5 is the b, and 2/5 is smaller than 1. Then we have 1/2 to the x. 1/2 is the b because it's attached to your exponent, and 1/2 is smaller than 1, which makes this decay. So, two examples. So let's look at this first one by itself. So this one is actually exponential growth. And the way we find this out is if you read the graph starting from left to right, you would actually be moving up on your y's, which makes this increasing from left to right. So this is exponential growth. I can also tell from the equation. This is the b value because it's attached to the x, and 2 is greater than 1, which makes it growth. Now, we have a new part of these graphs. It's a dashed line down here at the bottom, right on the x-axis. This dashed line is what we call a horizontal asymptote. So what this is, an asymptote is a boundary line that the function will not cross or touch. Now, for our purposes now, the exponential functions have a horizontal asymptote always at y equals 0. Now, this isn't actually shown on the graph. It's not something that you actually see when you graph things in, let's say, a calculator. We know it's there, which is why it's a dashed line. It's kind of like an axis of symmetry. It's not actually shown, but we know it's there. Now, why is it at y equals 0? Let's talk about that for a minute. So I'm going to use this table to show you why it is y equals 0. So I'm going to use this table. So I'm going to substitute x's into 2 to the x and get the y value that results. So if I substitute a 1, 2 to the first is 2. If I substitute a 0, 2 to the 0 is a 1. 2 to the negative 1 is actually 0.5. 2 to the negative 2 is 0.25. 2 to the negative 3 is 0.125. 2 to the negative 4 is 0.0625. 2 to the negative 5 is 0.03125. 2 to the negative 6 is 0.015625. 2 to the negative 7 is 0.007813. So if you look at these y values, they're getting smaller and smaller as you decrease your x's, but you never actually hit 0. You're going to keep getting bigger and bigger decimals, which means you get closer to 0, but you never actually touch it. That's why we have an asymptote, a boundary, at y equals 0. So let's talk about our domain. So the domain is always dealing with x values, so furthest left to furthest right. Well, this will go left forever, so we say that's negative infinity. Then the furthest to the right is the other side of your graph. Yes, that goes up, but he's also going to the right forever as well. So we have negative infinity less than x less than infinity. So we say that that is all real numbers. So I can have any x that I could possibly think of. Range, on the other hand, that's your y values. So the smallest y value, this arrow actually will not go down forever. He's going to get closer and closer to 0, and then he's just never going to pass 0, but he's also never going to touch y equals 0. That's why there's an asymptote. So it's 0 less than, because I can't be equal to it, y. Now, furthest up is this top arrow again, and that will go up forever, so less than infinity. So if we turn this around, that really means that you will have every y as long as you are greater than 0. This is your domain and range. It will never change. This range, or this domain and this range, are always going to be the same for these exponential functions. Now, let's talk about exponential decay. So, same idea. We know that it is exponential decay because if you read your graph from left to right, you are actually decreasing, so you're going down a roller coaster. This is the decay. We can also tell from the equation, because this 1/2, that's the b, because it's attached to your x, is smaller than 1, which means it's exponential decay. You are decreasing. This also has an asymptote, that boundary line at y equals 0. This also has that. Now this is going in the other direction, but it's generally the same idea. So if I do the same thing with this table, trying to show you why it's not going to pass 0, this is 1/2 to the x. So I'm going to substitute x's in and evaluate. So if I plug in x is 0, I get a 1. If I plug in x is 1, I get 0.5. 1/2 squared is 0.25. 1/2 to the third is 0.125. 1/2 to the fourth is 0.0625. 1/2 to the fifth, 0.03125. 1/2 to the sixth, 0.01562. 1/2 to the seventh, 0.00781. So again, as you see, when this starts getting flat, the further higher your x's go, the closer to 0 you become, but you'll never actually hit 0 or pass it. So again, let's talk domain and range. Domain is all of your x's, so that's furthest left to furthest right. So furthest left is on the left-hand side. This is going to be going left forever, so we say negative infinity, less than x, less than. Furthest right is this arrow, and it's going to go right forever, so we say infinity. So even for decay, your domain is still all real numbers. Then for the range, that's your y's. Again, smallest to highest. Your lowest y is that boundary of a 0, but you're never going to hit it, so we have to leave it as just a less than. Then the y. Then your highest y is this arrow up top, and again, you will go up forever. So if you turn that around, it's still y is greater than 0. So exponential growth and exponential decay have the same domain and range. Just one is increasing and one is decreasing. So let's look at some graphical examples trying to figure out if this is growth or decay, the initial value, horizontal asymptote, domain, and range. So let's start with, is this growth or decay? So we read our graphs from left to right. So if we start at the left and we follow our graph, we notice that we are going upwards. So that means this is exponential growth. The initial value, that is that y-intercept. It's your starting point. So the y-intercept for this graph, the initial value is 1. Now to find the horizontal asymptote, you want to find where does your graph start straightening out. So here's where it starts straightening out left to right, and it kind of gets close to that axis. Now, yes, it looks like it touches the axis, but we can't make the graphs extremely accurate. So our horizontal asymptote, that's this red line, I'm going to say HA, horizontal asymptote, is y equals 0. Y equals because it's horizontal, and 0 because it approaches the x-axis, which has a y value of 0. Now for domain and range. So domain is your x's. Well, it's going to go left forever, and it's going to go right forever. So left and right, both infinities, means you have a domain of all real numbers. Your range is furthest bottom to furthest top. That's your y's. Well, my lowest is that 0, that boundary line, the asymptote, less than y, because you're not going to ever hit 0, you're just going to get really close to it. And then less than infinity, because it will go up forever on your graph. So if we turn that around, y greater than 0. Example 2. Is this growth or decay? So it is decay, because if we read left to right, we are falling. We're going down the roller coaster. So this is decay. The initial value is still the y-intercept, so it's still this point here. This is the initial, which is a 1 in this case as well. Horizontal asymptote, that's where does your graph start getting really flat. So it's right here on the x-axis. So it has a horizontal asymptote of y equals 0. The domain, furthest left to furthest right. So furthest left is negative infinity. Furthest right is infinity. So you have a domain of all real numbers. Then your range is your y's. The lowest you can go is 0, less than y, less than, but the highest I can go is infinity. So y is greater than 0. Number 3, growth or decay. So again, read your graph left to right. We are falling again, so this is decay. The initial value is the y-intercept. Where does the graph cross the y-axis? So this is your initial. Notice it's not 1 this time. It's actually 1, 2, 3, 4, 5, 6, 7, 8. Initial value of an 8. And the horizontal asymptote is, again, where does it start becoming flat and then go all the way across? So we have y equals 0. Domain and range are not going to change. I can still move left forever and right forever. So my domain is all real numbers. And my range is everything above this horizontal asymptote of 0. So y greater than 0. Now let's look at some equations. So the general equation, I'll write it here for you, is y equals a times b to the x. The a is the initial value, the b is the growth or decay factor, that number that's attached to the exponent. So if we look at number 4, first it asks us, is this exponential growth or decay? So we need to look at our equation. So to figure out growth or decay, you look for that b value, so whatever's attached to the x. Well, that's b. Since 4 is greater than 1, that means it is a growth. So the growth or decay factor is a 4. Now, the initial value is this a piece that's multiplied to b. I don't see a number multiplied to b, but you have to remember there's always a 1 multiplied to stuff. We just don't write it. So if you don't see an initial value, it's always a 1. Well, g of x equals 2 times 3 to the x. So first off, growth or decay. Well, the 2 is the a, the 3 to the x is the b because that has the x attached to it. So 3 is greater than 1, which makes it exponential growth. The growth or decay factor, that is your b value. So in this case, this would be 3. And the initial value is your a, and we have a being 2, so that's the initial value. H of x equals 2/3 to the x. So growth or decay, well, we need to find our b for this. So this is that b value. B is equal to 2/3. So 2/3 is smaller than 1, so that means it is decay. The growth or decay factor, that's also b. Well, that's the actual number. It's 2/3. The initial value, that's your a. That's the y-intercept. Since it's not showing an A, that means there's a 1 in front of here that nobody writes, and that's the A. So we have an initial value of 1. Number 7, j of x equals 1/4 times 5/2 to the x. So 1/4 is in the A spot. 5/2 is B because it's attached to your exponent. So 5/2, well, that's greater than 1. Just because it's a fraction doesn't mean it's smaller than 1. 5/2 is actually 2.5. So that's larger than 1, which means it's exponential growth. The growth or decay factor is the 5/2. And the initial value is your A, which in this case is 1/4. 8. 2/3 times 5 to the x. So this doesn't have parentheses, but 2/3 still does not have an exponent, so that's your A. 5 to the x, that has your exponent, that's your B. So because the 5 is greater than 1, that makes this exponential growth. The growth or decay factor is the 5, and the initial value is 2/3. 8 times 1/4 to the x. So 8 does not have the exponent, so 8 is your A. 1/4 to the x has the exponent, so that's your B. So that's your growth or decay factor is the 1/4. Now, 1/4 is smaller than 1, which makes it decay, and the initial value is 8.